Hello and welcome to today's demo and discussion on external building aerodynamics specifically for pedestrian wind comfort. Today I've got a few slides to start. We're going to talk about the application example in particular, what we're going to be showing today. And then we're going to be moving over to the SimScale platform and doing a quick platform demo to show you the workflow and what the results look like, and then we'll come back to the presentation for some final conclusions and discussion on some results. So my name's Darren Lynch. I'm an application engineer here at SimScale. I've been here for about 3 years, and in the last couple of years I've been working more specifically around external building dynamics on the lattice-Boltzmann method. So here is today's agenda. These are the kind of topics that we're going to hit on today. Starting with an introduction to pedestrian wind comfort, an intro to lattice-Boltzmann method and pedestrian wind comfort, the demo itself and how we set that up, and then finally a live discussion, a live demonstration. Pedestrian wind comfort is the name given to analysing comfort around an urban area on a pedestrian due to the effects of wind. The buildings that we design can drastically affect this comfort, where many wind interactions with those buildings can cause windy conditions at pedestrian level. And CFD can actually be used to assess these effects, and SimScale has automated this process to make it as easy as possible whilst maintaining many controls required to cater to the variety of scenarios. And we'll show you how we do that in the next couple of slides. So introducing the lattice-Boltzmann method. Lattice-Boltzmann method is actually powered by a solver called Pacefish, and it's got many advantages that traditional CFD methods don't have. Okay, so the first thing is it's robust, and when we talk about robustness, we talk about handling of CAD models, and more specifically CAD models with faults. We deal with that a lot when we have these large city models where there are sliver faces, intersections, there might be openings, it's not watertight, and you know, when you've got just this much geometry, you expect some sort of quality defects. Now, for traditional CFD methods, you would have to go and clean all that up, make sure that it is watertight, but with the lattice-Boltzmann methodology, you don't need to worry about that. We have automated specifically for external building aerodynamics. So we've got the lattice-Boltzmann method, but we've also built a wrapper on top of it that automate the process for pedestrian wind comfort and external building aerodynamics. And this means that we've simplified it down to 3 simple steps, and we'll be going over these steps in more detail later on in the presentation. But as an overview, what we're doing here is defining all of the complicated CFD inputs by asking you some simple industry-specific questions like, where in the city are you interested in solving, whereabouts on Earth are you actually solving this problem, and where are pedestrians actually standing. And they are the specific questions that we actually ask the user to provide. Thirdly, it's incredibly accurate, and not only accurate, it's incredibly fast as well. So having both of those in the same solver is rarely seen. The accuracy here is displayed using the ARJ case E, and we're comparing experimental wind tunnel results with SimScale's lattice-Boltzmann method, or the lattice-Boltzmann method powered by Pacefish. And you can see there the Pearson coefficient is 0.86, which is high. Okay, and finally, I did briefly touch on this. It's fast. So the code is written on to make best use of GPU processing power. That essentially means that we can run these transient analysis types in under a couple of hours. So where a traditional open foam in steady state might take a couple of days to solve 50 million cells, we can actually do that in transient in a couple of hours tops. So it's a real improvement over a traditional CFD. So let's talk briefly about today's demo. So what we're talking about now is what I'm going to be showing you on the platform itself, and we're looking at a small city section in Bristol. So this particular city section is just to the north corner of Castle Park, and it is 300 metres by 300 metres approximately, and it is incredibly high detailed and provided to us by our partner CAD providers, AccuCities, and I do encourage you to go and check their geometries out on their website. And you can actually see how good that similarity is on the right hand side there. So there is incredible similarity between the CAD model that we're using, which is on the bottom, and the Google Earth image that I've just captured on top there, even down to the right use designation. So the green grass is designated correctly in the model and real life. Also, the tree positions are very well positioned, and the building detail is incredible. So that's what we're going to be using for our demo, and we're going to be discussing how we set this up in the SimScale platform. And the objectives are to show the pedestrian wind comfort in the city area, where pedestrians are going to be walking and doing activities, but also to show how highly detailed geometries from AccuCities are a great fit for the pedestrian wind comfort workflow. And as I mentioned, I do encourage you to go and check out AccuCities' website, and some more details are on this slide here, and the link in the previous slide. So let's discuss preparation. So did we just take the geometry from AccuCities and plug it straight into the SimScale platform, or did we do something in between? And the answer is we did something in between. So what we've got to do when we create geometries for the SimScale platform is to make sure that if there is a topology that is something representing hilly or rough surfaces, then we've got to make sure that it is A, represented in the geometry from AccuCities itself in this case, but B, it extends out past the wind tunnel boundaries. And to do this, the best way is to just take the border of the topology that we've got, in this case it was a square, and extend it out to some circle that centres around the middle of the geometry. Now, it depends on how big your geometry is to how big your terrain extension should be, but as a general rule of thumb, if you extend it out to 2 to 5 kilometres, you should be good and well in the clear. And the reason why we do this is kind of labelled up at the top right, so you can actually see this terrain. It cuts the wind tunnel, so imagine this is a wind tunnel placed around the geometry. What you want to do is make sure that air is only going over the surface and passing the buildings. You don't want it going under the surface or popping up within the domain unexpectedly. So back to the SimScale workflow. How does this actually get defined on the SimScale platform? And we're going to be going through this live together anyway, but in general we define a region of interest. Now this means that we select a disk, and that disk represents where in the city that we're actually interested in. So this might be a tight disk around some development zone that you've designed, or it might be around some sort of park that you're trying to landscape. Try and make it as tight to your development as possible, whilst allowing for the results to be output in the near surrounding area. So anything that could be influenced by your development. Next up, we would define a windrows, and that means weather conditions. And in the SimScale platform, this can be uploaded using your own data, but actually you don't need to do that. What you could do is you could just type in your location and import wind data from our partnered service, MeteorBlue. And MeteorBlue provide wind data from all around the world. So you type in a location and you get a very exact coordinate result. So this is as simple as typing in your location and importing weather data, and it's done for you. And then define pedestrian zones. So where are pedestrians actually walking around the city? And typically you can see actually in the picture it's highlighted blue. And that is where I've selected all the surfaces on the ground level. Now, that doesn't have to be so. Pedestrians could be standing on balconies or terraces or other high up surfaces, and you can just select those as you see fit and as you need, and they will also function perfectly as well. So let's hop over to the SimScale platform for a short live demonstration. And when I say live demonstration, we're going to be taking the exact same project that we've just been discussing, and we're going to set it up in real time. So hopefully you're seeing my screen now. What we've got on screen is the geometry with some results actually animating here. So we're seeing some streamlines, some particle traces around one of the higher rised buildings in this region. And as a brief introduction to the SimScale platform, we've actually got the viewer, which is this space, this large space in the middle, and this is where you see results, but also interact with your geometries, make graphical assignments, and you can also inspect anything that you've actually done to the model. On the left hand side is what we call the simulation tree. So this is where we go through and we actually set up the simulation. So all of the parameters that we're defining about the simulation is defined in this area. And typically speaking, we work in a checklist kind of workflow. So we work from top to bottom, checking off all the things that we need to do, and then at the end we can run a simulation. And that's the workflow. And of course, if you wanted to upload your own geometries, it's located in this area here. So geometry uploads are located here, and I do recommend for this type of analysis an STL model is the most robust. You can of course also upload many other file formats, including Revit and Rhino as well. Excellent. So with the SimScale platform introduced, let's go ahead and start setting up this particular simulation from scratch. And typically this only takes a couple of minutes, so if I wasn't talking whilst I'm setting it up, we could do this in 2 minutes, but let's take it slowly and explain what we're doing in the platform. So first thing I'm going to do is come along to simulations. I'm going to create a new simulation, and you can see all of SimScale's capabilities are listed here, and the one that we're particularly of interest in is Pedestrian Wind Comfort. Also, whilst I'm here, I will just point out the incompressible LBM that the Pedestrian Wind Comfort is based upon is also available in its raw form. Okay, so I'm going to create a new simulation. We can see that the latest geometry is selected by default, and we're going to go ahead working our way down this checkbox system to make sure that we've set everything up. So the first thing that we come to is geometry, and we know that we're using the correct geometry because it was the latest one that we uploaded. So we can move along to region of interest. So by default it's 300 meters radius. What we're going to do is change that to 150 meters because the city block itself is only approximately 300 meters by 300 meters. So I'll go ahead and change that. There we go, and you can see that is much tighter on the geometry that we've uploaded. And in this case the center point is located on 0, 0. I know that from the CAD, so I'm just going to change this to 0, 0. And that is all we need to do to define the region of interest, and I can save this now. Now we can move on to the next thing, and we notice that the thing that we really need to do is denoted by red, and that is because at the moment wind conditions is completely undefined. Previously region of interest was actually defined by default, but wind conditions was completely undefined. So what we're going to do is we're going to type in the location of this geometry and automatically import from Meteor Blue our wind results. So Bristol is our location, and we select it from the top of the drop down list, and we can import wind data. And I did mention Meteor Blue before. This is the little symbol down here just to tell you where it's coming from, and I can import that data using the big blue button. Now at this stage I could also turn down the number of directions if you like. So I might not want to go straight in and solve 16 wind directions. I might just want to solve a quick simulation for an early stage analysis and just understand really what those results are telling me about my design. So I'm going to change this to maybe 8 wind directions. That would be good for a demo. Also to note, because it gets asked quite a lot, is that you can change the wind exposure categories under this drop down list here, which means that you can tell the solver what the surrounding environment is actually like. So in most cases, and in this case, all of the directions are urban area 4, and therefore we would go and select urban area 4 for each direction. And finally, we want to define what the pedestrian comfort map is. So where are my people standing? What are they going to be standing upon, or more specifically? So we can create a new comfort map, and we could go through and select graphically all of these faces that pedestrians might be standing on, which for a small amount of faces might be a good workflow. But actually in my case, what I'm going to do is I'm going to select it from the geometry tree on the right hand side here, which we haven't introduced yet. So when I uploaded STL in layers, all of my layers appear here, and this is where I'm going to select my layers from. So I'm first going to scan through and check which ones pedestrians might be standing on, starting with green spaces, then moving along to man-made surfaces, roads, terrain patches, terrain, and that's all. There we go. So we're fully defined there. And we can also change the pedestrian measure height. So if pedestrians are actually walking around at, if we're actually measuring pedestrian comfort at 1.5 meters, then that is a default value that is defined. In some places in the world, 2 meters is preferred. Alternatively, if you're looking at some sitting area in a pedestrian zone, then you could also have a lower value of that as well. But I'm going to leave it as default and press save. Now finally, we are actually ready to go, so we could actually start a simulation right now without having to do any more. But it's important to note at this point that you can of course do many other things, and you have got control to do many other things, such as defining surface roughnesses. So you could set the roughness of grass or gravel, roads, buildings for example, and build that definition up. Alternatively, we've got porous objects, which notably has a tree option where we could define all of these trees in the city region as well. And that is obviously some functionality that should be used in the final and next steps of this simulation. So I'm going to create a new simulation. Now notice there, it hasn't given me any warnings or any errors, which means that we've set this simulation up exactly how it expects us to. What it would have done if we had missed something or done something incorrectly is it would have notified us and allowed us to go back and change that. So it's a really fantastic sanity check before we actually commit to running any simulations. And also at this stage it gives you a good estimation of how long it's going to take. So that's an estimation in terms of duration, compute resources, mesh size, but also minimum cell size, so approximately 60 centimeters in this case, so it's actually a good resolution. And once we're happy with that, we've renamed it something relevant. I'm just going to leave it as default, but something relevant will be helpful. We can actually start the simulation. And once it's started, you'll see a little progression bar, and we'll start having the processing being displayed. So it'll tell you anything that solvers or anything relevant from the solver, and it'll also tell you how it's progressing, how many minutes it's been running for, how many GPU hours it's run for. Now I'm not going to wait until the end of the simulation. I'm of course going to go and show you one that I made earlier, and I'm going to show you where to find some of the key results before we move back to the presentation. So here's one I made earlier, and if we scroll down to the bottom where simulation runs appear, we can see that there's a little green icon now where run 1 is. Now that means that the simulation has run, it's complete, and it's got results. So that's what we're going to analyze. So the first thing we're going to do is we're going to look at the statistical surface solution, which basically holds all of our comfort maps, our safety maps, for many different standards. Now, whilst this is loading, just to note that, of course, if you're using SimScale on a daily basis, you've also got chat functionality. So if you need to get hold of us to discuss any of these parameters, or you're having troubles with something, or you can't find some documentation, you can actually reach out to us through this live chat. What you could also do is share the project with us, which allows us to also come in and look at the project in real time with you and actually decide on what the best course of action is or next steps. So much better than the traditional off-shelf answer or tickets that you have to create with more traditional computer-aided engineering providers. So we've got our results loaded into the viewer. And what we can see is a colour map. So this colour map is representing the comfort, and in this case the comfort in terms of the Lawson LDDC comfort criteria. And as you would expect, blue is actually quite comfortable and red is uncomfortable, and anything in between is a range. But actually that's one of the major misconceptions, is exactly that reading of the results. Actually, what we've got to do is actually consider the activity in which we expect a pedestrian to be performing in certain areas, and then see if the comfort level is acceptable to that activity. So it's not just a case of varying discomfort, it's more of a case of matching your activity to comfort levels and seeing if it's acceptable. So for example, if there was a sitting area in this area here, there isn't, just trust me, but if there was, then we could say that these pedestrians are going to be comfortable outdoors dining near that restaurant. So this area is actually suitable for activity. Now, in contrast, if there was a pedestrian crossing in this area, we would be expecting people to be standing at traffic lights waiting for the lights to change. And you can see that actually they might not be comfortable doing that, because the minimum activity comfortable there would be business walking. So they could be walking across the pedestrian crossing quite comfortably, but standing there waiting for lights to change might not be comfortable. So that is how you would read these results. And what you can also do here is look at where results may be less comfortable and go into the results and identify why they might not be comfortable. And that's what I'm going to do next. So I'm going to go into some directional results. So you can see that here there's a directional category, and this directional category means that we're going to look at wind speed results and wind direction results for each of the directions that we've actually solved. So in this case we solved 8 different directions. So for each of the wind directions, say northerly, easterly, westerly, etc., we're going to get an individual set of results. And I'm going to load up the additional average results. And that's going to show you the same visualization that I showed at the beginning of this demo. So if I play this animation and close that, what we actually see here is the wind results around a key building from the southerly direction. And what we're after looking at here is trying to understand how wind is interacting with this building, where there is downwash, and also if there's any cornering effects that might be affecting the pedestrian comfort. Now, because this is quite a cylindrical building, actually this is not drastically affecting pedestrian comfort, but if we had a very different building with a very different shape, we might actually be seeing more of those dominant effects occurring. So at this point I'm going to hop back to my presentation slides and just finish off the results section. So final 2 slides on the key results. So these are the wind comfort maps that we saw earlier, and you can actually see here a better representation of what these these comfort bins actually mean. So what activities you would be comfortable doing, and it's graphically displayed there. And what we've also got is we've got some visual cues as to what activities could be comfortable in certain areas. What's good to know is that we do, of course, offer different comfort criteria which might be relevant for different parts of the world. So we do offer the Lawson LDDC comfort criteria, as I showed in the demo, but we also do Davenport and NEN 8100 as well, with a few more on their way to keep up with some new standards that have been implemented across the world. And on the left hand side there is a more detailed explanation of the legends that I briefly described. So not only have we got the colours that it represents, the categories that it represents, and also the most casual activities that is deemed comfortable, we've also got the wind speed bins that we're using to actually decide what's comfortable, and the probability of it exceeding. And this is straight from the standards in which we use for these comfort criteria. What we're going to do now is delve a little bit deeper into these individual wind directional results to understand really how to correlate this comfort criteria with wind speed results, and really identify some of the key effects that are going to cause discomfort within your results. So to start, we've got a list of 3 main items on the left hand side there, and what they are is downwash, cornering effect, and also the channeling effect. Now there's a different way to identify each of these effects based upon these directional results. Starting with downwash, the best way to identify a downwash is to look at the 3-dimensional results around some key large buildings in your development, and to actually stream those particles from some source in front of the building and see how they're impacting and moving around said building. And from this you'll be able to see how the wind from higher up in the atmospheric boundary layer is being washed down to pedestrian level and affecting the comfort results around the foot of the building. Moving on a little bit further, we can identify cornering effects by looking at the same comfort map level, but the wind speed results upon that, and looking around any sharp corners of a building. So sharp corners are going to cause flow separation around the corner, and therefore you're going to get wind speed increasing as it separates, but also a reduction of wind speed in this separated region. And that is quite evident just near this arrow here, where we've got that red region, which is actually high velocity, where it's separated away from the corner. And finally, the channeling effect. So a channeling effect typically happens when you've got 2 taller buildings next to each other with a gap. Now if pedestrians happen to be doing activities, either walking or sitting or what have you, in between 2 large buildings, then this is going to be a significant role player, because what wind will try and do is move around the buildings by passing between them, and this passing between them is going to be of increased speed quite significantly. And you can see that in the bottom left image there. So the 2 arrows, you can see kind of a combination of cornering effect there, but mainly channeling effect, where we've got those 2 large buildings with wind being forced between them. And they're the 3 main things that we're looking to understand from these 3-dimensional velocity results, and really correlating that back to your comfort criteria, where you can say, oh okay, so this area here is uncomfortable because of effect X or Y or Z, downwash, cornering effect or channeling effect. And we could do something to improve conditions there, such as putting some trees in. We could be putting some screens in, or even if you've got downwash, you could be putting some sort of canopy to stop the wind from washing down to pedestrian level. And that's actually the end of my presentation. So thank you very much for joining. Thank you very much for listening to me and following along with me. And if you've got any questions, then feel free to reach out to myself or the sales team if you feel this is something that could be used in your company, and we'll be more than happy to discuss it further. Thank you very much. Have a good day. Cheers.